So this presentation is on marginalization in Bayesian networks. And in particular, I will show you a method that allows to integrate exact and approximate inference. And just as a small remark at the beginning of this presentation, this topic is also known under the estimation of the normalizing constant, and it's generally discussed under this very broad topic of inference in machine learning and statistics. Now, before we start diving into the details, let me just briefly motivate why this topic is relevant. So assume that you have data that you want to classify into two groups. So as an example, as a practical example, that could be the mutational data of patients diagnosed with cancer, and these patients have different cancer subtypes. Now, if you want to use Bayesian networks for this kind of analysis, that is generally possible. However, if the data is subject to missing data, as is very commonly the case in biology, then you need to calculate the marginal probability distribution in order to be able to classify the data to each of the networks, right? So in order to work with Bayesian networks here, if you have missing data, you need to calculate the marginal probability distribution. And a method of how we can do this, I will essentially present you in this presentation. So before we talk about marginalization, let me just briefly introduce you to Bayesian networks in general, in case that you're not familiar with them. So they're currently the most popular causal model on the market. And a very nice thing about Bayesian networks is that they allow for a graphical interpretation of the probabilistic relationships that underlie the data. So a Bayesian network is usually associated with a directed acyclic graph, as shown here on the right. And in this directed acyclic graph, we have nodes that represent the random variables and the edges that essentially show the probabilistic relationships or model the probabilistic relationships in the data. Now, essentially there are two very fundamental challenges in the area of Bayesian networks. So first of all, and probably also most obvious, the challenge is to learn the structure of a Bayesian network, right? So how can we determine the structure of the underlying DAG in a Bayesian network? And that problem is generally NP hard. However, there has been a lot of progress in recent years on this topic that allows us now to apply Bayesian networks even in high-dimensional settings. Now, that essentially motivates the second big problem, which is marginalization. So marginalization essentially means calculating the probability of a subset of variables. So in missing data, you need to marginalize, and marginalization itself is also an NP-hard problem, meaning that in the high-dimensional settings that we can now apply Bayesian networks on, that is computationally challenging. Now, to be a bit more formal about this, let me just really briefly introduce you to the notation. So a Bayesian network is constructed of a directed acyclic graph of nodes V and edges E. So the nodes represent the random variables, and the random variables are associated with a probability distribution, right? So Bayesian networks in general, the combination of probability distribution and a directed acyclic graph. And the very nice thing about Bayesian networks is, or a very neat property, is that you have this factorization, meaning that the probability of the full set of variables, right, so the completely observed variables, can be written as the product of the probability of the single node given its parents, right? And that makes the use of Bayesian networks computationally very efficient. It's also known under part of the Markov conditions. And if you, however, now have missing data, then the calculation isn't so easy. So let me just very formally also define what we mean by marginalization, or the marginal probability distribution. So with the marginal probability distribution, we essentially mean the probability of sum of observed variables defined over essentially the sum over all of the unobserved variables, right? So the probability of the observed variables, that could, for example, be in this graph here on the right, the probability of the gray variables. So assume that you only observed E, the variables E, N, and O. And to determine the probability now of E, N, and O, you need to sum over all of the variables that are not in the observed variables, meaning all the white nodes here, right? And just as a convention, I will refer to those variables, to those observed variables, as evidence variables. And as you can probably see by the way that I've introduced this problem, this is an NP-hard problem, because to get the probability of E, N, and O, so of the evidence, you need to sum over all of the possible states of the non-observed variables, right? So if this problem is NP-hard, that essentially means that computationally it's not applicable in high-dimensional settings. And since it's always kind of a matter of taste of what we mean by high-dimensional, for some people, I guess it's 100 nodes, for some people it's 1,000. I've created this very high-dimensional Bayesian network where I think many of you will agree on the fact that this clearly is very dense and high-dimensional, right? So what I want to show here with this graph essentially is that in this setting, you cannot apply the simple equation that I showed you before for exact inference, right? So maybe going back again to this equation, it's very simple. However, if you want to apply it on a space like this, you would need the runtime. Your algorithm would essentially run forever, or a very long time, and that essentially would make the computation impossible in high-dimensional settings. So what people generally do now is they apply approximate inference on the problem, meaning that they approximate the marginal probability distribution. Now, in general, these approximate inference schemes essentially are applied on the full set of variables of the Bayesian network. And the key takeaway message that should come out of this presentation, key thing that I want you to take away, is that you don't need to do this, right? So there are ways to reduce the dimensionality of the problem that we solve by means of approximate inference. And how that works, I will present you on the upcoming slides. So first of all, let me just define an irrelevant node. So an irrelevant node is essentially a node that doesn't contain the evidence variables, and it also doesn't contain any descendants of the evidence variables, right? So here in the graph on the right, we're getting this gray node represents the observed evidence. Then C, for example, just as an arbitrary example, C would be an irrelevant node because essentially C doesn't contain the evidence, but also none of the descendants of C contain the evidence. Now, why is that interesting? Essentially, it helps us to define a relevant subgraph, and a relevant subgraph is essentially defined as the graph that remains after removal of all of the irrelevant nodes. And the neat thing about this relevant subgraph is that the probabilities, so the marginal probability distribution over the subgraph is the same as over the full graph, right? So without any complex steps, we were already able to remove quite a few variables here, but I guess in general, also kind of the key part that I want to present you is the next one. And here we essentially introduce the conditionally independent subset. So in a conditionally independent subset, you essentially have a set of variables that is deconnected within the set of variables. And all of the variables in the conditionally independent subsets are separated from all of the remaining variables, right? So here again, coming back to this example on the right, again, E, N, and O are the observed variables, so the evidence variables, and we can now separate this graph, or the variables in this graph, into two conditionally independent subsets. So S1 on the top and S2 on the bottom, and essentially the neat thing here is now that we can split up the calculation of the marginal probability distribution into smaller, more digestible parts, right? So if we do this and we apply this to the junction tree algorithm, for example, then we can reduce the complexity of the problem, because essentially, coming back to this example here, it's quite obvious that in an NP-hard problem, the complexity of the full graph or the full set of variables is higher than the complexity or the computational complexity of smaller subsets of this graph, right? So I just show you this in a practical example here in the junction tree algorithm. Consider this graph here on the left, which is constructed of these evidence variables A, D, E, and H. And essentially, if we get the moral graph from this directed acyclic graph, which is part of the junction tree algorithm, then typically you would need to introduce here in this particular example 5 additional edges in this moralization and triangulation step, right? So this is how the moral graph of such a Bayesian network would look like, or such a directed acyclic graph would look like. If we, however, apply the scheme that I showed you before and split the variables into conditionally independent subsets, then the moral graph would look like this here. So the moral graph here on the right. And here we only need to introduce one additional edge. And I think just by eye, it's already quite clear that the computational complexity of this moral graph on the right is much lower compared to the one here in the middle, right? So essentially, by splitting up the problem into smaller, more digestible parts, we can essentially apply exact inference on a very broad variety of problems, right? And there still might be the possibility that now some of the subgroups, so some of those subsets that are defined in your Bayesian network, right? So it might still be the case that some of these subsets are so large that you can't apply exact inference on them. But then what you can do is to apply exact inference on all subsets where it's possible, and then apply approximate inference on all variables where it's necessary, right? And that is essentially expressed here in this very lengthy equation. I'm not going to go through the details here. There is more details on that in the preprint in the archive, so feel free to have a look at it in case you're interested. But essentially, what I want to show here with this equation is that the probability of the marginal probability that the marginal probability distribution can be essentially expressed as the parts where you apply exact inference on, so the subsets where you apply exact inference on, and the other subsets where exact inference is not possible and you need to apply approximate inference, right? So coming back to this very high dimensional Bayesian network that I've showed you at the beginning, you can now essentially split up this high dimensional graph into smaller, more digestible parts, where on most of these conditionally independent subsets, it's actually quite easy to apply exact inference on. So if you look at these subsets, many of those are actually quite low dimensional, and there's no need to apply approximate inference on them, since exact inference is both fast and also exact, so there's no error introduced. So there's still some groups that remain where you apply approximate inference, but it's essentially not the whole set of variables. That essentially has the benefit that it has a much lower variance, because essentially with each variable where you apply approximate inference, you introduce an error into the approximation of the marginal probability distribution. Right, so in theory, that essentially leads to lower variance. There's also the proof of that in the preprint, if you want to see that. And we also had a look at the benchmarks, which is obviously a bit more of practical interest. So essentially, we compared it to the Gibbs sampling scheme and the loopy belief propagation, which are essentially very prominent representatives of both MCMC and variational inference. And maybe just a small remark here, we did use the importance sampling algorithm at the end of the calculation of Gibbs sampling and loopy belief propagation, because essentially these two algorithms give the probability of a single variable given the observed variables. and that is different from the marginal probability distribution. So to account for that, we used importance sampling. So looking at this comparison, which essentially shows the normalized root mean squared error, so low in the comparison is better, we see that loopy belief propagation performs better than Gibbs sampling, and it's in particular interesting to look at the difference of loopy belief propagation and our proposed subgroup separation scheme, which is here shown in yellow and blue respectively, because essentially the underlying approximate inference part in our subgroup separation scheme is essentially the same as in loopy belief propagation. So the increase in accuracy that we see between the yellow and the blue line is essentially purely due to the proposed subgroup separation method, right? And so we essentially benchmarked this over a quite large range of different problems, and consistently we saw a better performance in the subgroup separation scheme. So if you're interested in seeing those benchmarks, it's included in the archive paper. And at the end of the presentation, I also want to come back to the application that I've showed you at the beginning. So essentially here we look at an application where we want to determine the cancer subtype of patients diagnosed with kidney cancer. So in particular, we're having a look at Korean population studies of cancer patients or patients diagnosed with renal cell carcinoma, which is the most common type of kidney cancer. And in particular, these patients were diagnosed with clear cell RCC and papillary RCC. So these two subtypes. So this data is subject to missing data. So only 26 of 70 genes were observed. And in order to account for that, we used the marginal probability distribution as proposed in the method shown here. And essentially using this, we were able to determine 76% so we were able to classify 76% of the patients to the correct cancer type. And just as a reference, if data would be complete, so if we were to observe 70 out of the 70 genes, then 83% of the samples would be assigned to the correct cancer subtype, right? So that can be sort of seen as an upper bound of the calculation. And then obviously, if we were to completely neglect the genes from the analysis, instead of imputing for them using marginalization, then we would have a lower accuracy of the calculation, which is 68% of the samples assigned to the correct cancer type, right? And we can also see this visualized here on the right. So here we have the probability of each sample, or the probability of the cancer subtype of each sample, shown here on the x-axis. So on the x-axis, we have the CCRCC and papillary RCC samples. And here on the next slide, we have a comparison between the probabilities calculated using marginalization and the probabilities calculated if we were completely completely neglect the variables from the analysis. So we see here an increase in the accuracy, both on the left plot here, but also here on the RC curve on the right. And since we discussed missing data now, I just want to point out in the end of this presentation that currently in Bayesian networks, missing data is often handled via imputation, right? So we impute the values of the unobserved variables given the observed variables, and then treat the data as if it would be fully observed. Now, that is essentially different from what we calculate in the proposed method here, which is the margin probability distribution, right? So that is the probability of the observed variables. And that also essentially shows, so this imputation also shows why a lot of the inference algorithms that are on the market essentially calculate the probability of a single variable given the observed variables, because you want to impute the probability, or you want to impute the unobserved variables. So this imputation essentially has a few drawbacks that I want to mention in the end now. So in the discussion on the relevant subgraph, we essentially saw that a lot of variables don't contribute to the problem at hand, right? So here in this example, where E, N, and O are observed, then if we impute the string of variables that is not contributing to the probability of the observed variables, we essentially introduce an unnecessary sampling error into the problem, because essentially none of those variables, so even though we can impute them, the imputed variables will be meaningless for the problem at hand. And another drawback of imputation is essentially that for each variable that you impute, you also introduce a sampling error, right? So instead of imputing the unobserved variables, it would be much more reasonable to calculate the probability of the observed variables using marginalization. Right, so, and that is also something that we think is going to increase the accuracy of missing data structure learning. And that's essentially also something that we are currently working on. So with that, I want to conclude. So this presentation has been on marginalization in Bayesian networks. And in particular, I showed you an efficient method that allows to calculate the marginal probability distribution. And that will be useful for handling missing data in Bayesian networks, right? So essentially, I don't expect you to go through the math yourself. So there's an R package available called Subgroup Separation. And at the end, I also want to mention that this method is essentially presented as a general framework that can be generalized to other exact and approximate inference schemes. So with that, I thank you for your attention. As I mentioned, there is a preprint available, and the code is also available in GitHub, where you can find the benchmarks and the reproducible application. And at the end, I also want to briefly thank Nico Behrenwinkel, Jussi Moffer, and especially Jack Kuipers for their contribution to this work. So with that, thank you for your attention.